sort of when you first learn something, it does seem like there's these equations that you get, and then you can apply the equations and you can figure stuff out. But this is just it's Feynman. It's a much deeper way of thinking about nature, many more connections at a much more physical level. And that really that made a big impression on me.
In this episode, we explore the inspiring journey of Professor Lyman Page, the James S. McDonnell Distinguished University Professor of Physics at Princeton University. A luminary in observational cosmology, Professor Page has been pivotal in deciphering the cosmic microwave background radiation, thanks to his leadership role in the Wilkinson Microwave Anisotropy Probe Project. His groundbreaking work has not only expanded our comprehension of the universe's origins, but also earned him multiple prestigious accolades in the field of physics, including the 2018 Breakthrough Prize in Fundamental Physics. We talk about his fascination with physics as an undergrad and his unique path to academia, which included a period of sailing and self-study after his undergraduate studies. This adventure led him to MIT, where he began working for free before officially joining their graduate program to research experimental cosmology. Page's story continues with his move to Princeton, where he not only advances research, but also served as department head. Throughout the conversation, he reflects on his teaching approach, the challenge of fostering diversity in physics, and potential strategies to address it. This episode offers a glimpse into the life of a physicist who combines passion for discovery with a commitment to education and inclusivity. Thank you so much for agreeing to be on this podcast, Lyman.
My pleasure.
So I interviewed you a couple years ago, and it was for something completely random, but when I talked to you, I heard this amazing story about your trajectory. And I was just like so mind blown. I thought it was so inspiring and amazing. And when I would talk to other grad students, sometimes we'd talk about things and I'm like, do you know Lyman's story? And they'd be like, no. And I tell them a bit about it. And I realized like this was such an amazing story. It should be made known to more people. This is like one of these stories, what kind of inspired me to decide to kind of like make a podcast and talk to people about these type of things. So yeah, no pressure on giving an amazing story. But yeah, I guess I wanted to dig into sort of like that path again. Mm-hmm. And I guess when you told it to me, I think it started off in undergrad. And, like if I remember correctly, you weren't a physics major. Mm-hmm. But then you decided to do physics, and then all these crazy things. You sailed up on a boat to MIT. So I don't know, where do you want to start? If we can.
Sure. That's probably good. Let's see. So shall I just talk on?
Yeah.
Okay.
Yeah.
So let's see. So I went to Bowdoin College up in Maine. It was the only school I got into, so that worked out. And then. Let's see, I started off as I started off as a philosophy major, and then that quickly merged into philosophy and English. And then I took anyway, that was sort of my path.
What made you pick philosophy?
Oh, I think probably just, answering the questions about the way we think and what we know, and even then epistemological questions and just general interest. I mean, I'd read The Republic in high school, and I just liked thinking about what it said and what it and how we were sure about things, and so it seemed good. And then English seemed like it was getting at a lot of the same questions from the human side, and a little less, not so much how we know what we know, but just sort of how it relates to human interaction. Anyway, so that was going along. I don't know if wouldn't say I was particularly good at it, but I was enjoying it. And then I took a physics course, and I just loved it. And it was a really simple course. I'd say not quite at the level of our Physics 101, 102. It was sort of in that range. Anyway, I thought this is fantastic. And so I just, it took about one semester and I switched my major to physics.
Oh, wow. What about it was so fantastic that made you just like leave all these epistemological questions?
I think what grabbed me at first was just being able to describe the world mathematically and sort of the if you will, certainty of it, and and that you could just describe nature so completely, and then just when we got little tidbits of questions, like this, you could see a problem. These are all simple first semester problems. You could sort of see it, and you could see how you could go further. And then certainly in high school and all that, we heard about these deeper questions, and heard about relativity and general relativity and quantum mechanics and all that stuff, and probably because I could do it.
Yeah.
Right? It was just as like, oh wow, I can actually do this.
Yeah.
The math I always took a math class, so I was not bad in math. Anyway, it just all made sense. And it was it was taught by Elroy Lacasse, and it's kind of funny because I had physics in high school and it was absolutely horrible. It was,
okay.
It was just we just would go to class and sleep. It was just so boring. But there's just something about this class that clicked, and
so you think the teacher was very influential?
Completely, yeah. That was it. And he wasn't that dynamic. He was. I thought he was old then, but he lived many, many more years. And he was just a classic, physics professor from a liberal arts school, and just talked in front, just lectured with chalk and in his tweed jacket, and made really dumb jokes, and but he was anyway. Something there just clicked, and that was it. So then and it really happened pretty quickly, and then never looked back.
Never turned back.
I always liked that. Yeah, no, and then I started taking more physics courses, and I went to the library early on when I started to get a taste of it, for physics, and I just walked down the library rows and I'd pick out books and say, that's pretty interesting. Just look at what could be known,
right?
And
because it's hard to, when I walked on as a grad student, I hardly understand any of the books.
Right.
So what were you trying to do when you look at the books?
Just sort of get my head around the field, just what was known. And I completely agree, right? These are daunting,
Yeah.
and this math was way beyond me. But there were ideas, and one of the books I ran across was Misner, Thorne, and Wheeler, and gravitation, and I said, okay, that was really cool, and so. Then I
guess you interacted with Wheeler when he was here.
Yeah, when he was
okay,
many
cool.
years later. I have a funny story about that if we get to there. But then so then I designed a course. We had Bowdoin was a small department, but they were really open, and they let me design. I guess it's the equivalent of like 2 junior papers here or something like that. It's just an independent study course, and it was to just work through not the easy sections of Misner, Thorne, and Wheeler. And,
as an undergrad.
As an undergrad, yeah.
Okay.
So and I was taking differential geometry in the math department, and so just doing that and then taking the other, regular physics courses.
So wait, you switched in your first semester of undergrad?
It would have been my second, I think.
Okay. And
Yeah.
that was enough time
Yeah.
to start doing differential geometry in undergrad.
No, so that was later. I did. I didn't. I
okay.
took that in my. That was so. This is a. I jumped a year in there. So this was.
Okay.
I think I took that in my junior year, and that's when I did this self-study.
Right.
Test. Before then I took more, just standard physics courses.
Right. Right. Okay.
And then. And that was it. And I just. Just really started getting into physics, and getting into. And also, I'd always worked with things, worked with my hands, growing up, and I worked
with your
on sailboats,
carpentry,
exactly. And
did you get that from your parents, or you just picked it up on your own?
Just playing around down. I don't know, building forts.
Yeah,
and I worked in I worked in a bike shop.
Okay.
I started fixing bicycles from when I was really young. Actually, and even when I was in high school, I'd pick up some money fixing bicycles, and I helped start a bike shop.
Oh, cool.
That ended up doing pretty well, and so and then so I was always just like doing that, building things and fixing things. So then. So I kept, that was my independent study, and then I did a senior thesis on building Josephson junctions, of all things, which I now starting to use more again. And so I, did a lot of work in the lab then. We used borrowed equipment from Bell Labs, and anyway, just so it's pretty much typical physics major type things, but at a
is that like a lot for I guess my I don't know that much about how liberal arts colleges are, but that seems pretty advanced for an undergrad. Even when I think about Princeton, I guess I don't know what the experimental undergrads do, but that seems intense still.
Yeah, but
like, would you compare it and think it's advanced?
I was nowhere near as advanced as the students we have. I mean, it's just night and day.
Yeah.
I didn't know anywhere near as much physics, and the laboratory work may have been at the same level. I never got that Josephson junction to work, though, and I think it was just because we just had impurities in our niobium evaporation, but it was it's really different. As there are 5 physics majors, and I think I was maybe a couple of us. Well, actually, I didn't go undergrad school, but eventually would. And just, it's just downstairs trying to get this instrument to work, and that was it. So it was much lower key than what goes on here, and without the expertise around. Just more like I don't want to say, it was fun, but it wasn't quite. And I really wanted to get it to work. I was really motivated to get it to work. But I wouldn't say it was that. I guess it was moderately advanced for there, but not as advanced. And I really didn't know as much physics as our majors do when they graduate. And I'd say it's about a year behind.
I see. Okay. That makes me wonder, sort of a lot of the students here that take physics, actually I don't know what their goals are, but many of them are to go to grad school after. And I was wondering, in your cohort of 5, like, what was your intention when did you think about what you wanted to do with this physics degree, and were your peers also thinking about what to do, or it was just like, this is fun, let's do it?
I didn't think about. I mean, I applied to grad school, And
Right after. Oh,
yeah,
I know you did later on too. But,
yeah, no. So
yeah.
when I was a senior there, it's a funny time. So I applied to grad school. I took the GREs. I did all that usual stuff. I did horribly on the GREs, and part of it was, well, I just didn't know that much physics. That was true. It was an attitude too. There's no way I was going to study for them or anything like that. It just wasn't in. It didn't think about the world that way, and
Yeah.
said, I could do this. And anyway, I did horribly on those, and applied to grad school, and didn't really know what I wanted to do, and then my girlfriend broke up with me, and then so there I was, a senior, and I got into a couple of places for grad school, I think, because I had good recommendations. I mean, I ended up graduating with high honors in physics, so that was it wasn't too shabby, but
Yeah.
but it was I'd done this experimental work, but it just wasn't a good match. I didn't see that working out.
Yeah.
So I applied to this. I went downstairs on, we used to, all the information used to be transmitted on like flyers that would get posted on bulletin boards, right? So I went down, and there was an advertisement for a research technician job in the Antarctic. So I said, that's for me. So
Wow.
so it's like bummed out, blah da da. I thought I can do that. So I applied, and they accepted me.
Oh, nice.
So that's what I did after college. So I went down, and I was a research technician in the Antarctic.
How many people were there? Well, what was that like?
So, oh boy, so our base, I used to know the number. If I remember, it's around 50. It was a Navy base then, and so I was at McMurdo Sound, which is on the coast, and then went to the pole to do an experiment, and then back to the coast, back to McMurdo to winter over, and then back to the pole to do another experiment, and then McMurdo, and then left.
Okay, how long was that?
I think that was about 13 months, and
Was that a cosmology experiment also, I guess?
it was cosmic rays, and so just because it was a good station, just because of the the field configuration. So low energy cosmic rays, right? They can come down the field. So we're looking for solar activity.
Okay.
And there were actually a few experiments. There's the cosmic ray experiment, and then there was a relative ionic sphere capacity measurement. And the cosmic rays, we'd look for muons, neutrons, protons, all that stuff. So, and then sort of the fun, and that was really taking care of a station, and it was recently the lab has been removed, but it was a mile outside of McMurdo Base, so I lived by myself in this Navy hut, maintaining this equipment, and then I'd drive in to town to get meals and see people and socialize and things like that, but and it was so beautiful. It was near the solar maximum, and we just see these incredible aurora.
Oh, wow.
Oh, it's just aurora that would cast shadows, and you'd see them across this expanse of frozen sea and these huge mountains in the distance, and it was just beautiful. And
So it looks like what you see when you Google aurora.
oh yeah.
Okay, because people have told me that there's a long exposure, and that's not what you see.
Oh no.
So.
No, they were dynamic. That's the thing
Oh,
that you
wow.
don't capture. I mean, they're undulating.
Yeah.
And then you'd see there were times when it was just like spears of light coming down from the heavens in the ice.
Oh, my.
And you could, it was like you could, in your mind, you would hear them, right? You can just crashing into the ice, and you could tell the New Zealand base, the Scott base, the Kiwis, had dogs, and I don't think they do anymore. They had sled dogs. And you could tell when the aurora were really going and they were a mile away in the other direction from the Navy base. The dogs would start howling. And then you'd get out and they'd be this howling and this incredible light show. Oh, it was beautiful.
Now I want to go.
Yeah. No, it's you have to go in the winter. It's a long stay.
Okay.
So anyway, it was beautiful and stunning and a good time to think about life and a lot of things, that sort of thing. And
Yeah.
so then we did that, and we did an experiment, probably I think it may have been the first telescope at the South Pole. We were looking for solar oscillations.
Of what?
There was a model that the sun had, I think it was 160-minute oscillations instead of 5-minute oscillations, and that would have implications for the structure of the sun. But there was, this is with a collaboration. My mentor there, my boss, was Martin Pomerantz, and there was a French group, Grec and Fossat, who built there's a little 4-inch telescope which just monitored the sun, and we'd look at the sodium D line, and from looking at the sodium D line, we could measure the velocity of the surface integrated. And so we could then look for these oscillations and just found they didn't exist.
Okay.
And so that was, put those theories to bed. Of course, all that analysis happened after me. I was long gone, but
okay.
But I was just I was a technician on that.
Yeah.
So that was another great experiment. We lived. We didn't want any local perturbations because you go to the pole because the sun just goes around, so you can look for long-term oscillations, which would normally be biased at a higher latitude site. But we didn't want any local perturbations, and so we took a cargo container and buried it under the snow. in 12-hour shifts, it'd be me and Pomerantz, and then Grec and Fossat, and we'd shift and make sure and just take data.
Oh, you just have to monitor it. You have to be there in case something goes wrong?
Yep.
Okay, I see.
So we would drive the snowcat out, be under there. But
everything was automatic still, right? Like it was just computers collecting.
Yeah.
Okay.
Yeah.
Okay, yeah.
And then so we did that experiment, and then back to McMurdo, and then. But one of the things there I did is I read the Feynman lecture series.
Mm.
And that was, I read a lot of physics down there and just read textbooks and did problems. And it was when I did that, then I think I realized how it was awakening for me, how little physics I'd really learned as an undergraduate.
Yeah.
Even, learning the same things, just again, in a new way,
right.
in a much more physical way. And, much less, sort of when you first learn something, it does seem like there's these equations that you get, and then you can apply the equations and you can figure stuff out. But this is just a much, it's Feynman, it's a much deeper way of thinking about nature, many more connections at a much more physical level. And that really, that made a big impression on me.
Yeah. I remember you said this last time too, and it's made me wonder. Sadly, I haven't gone and picked up these books, but I think in our curriculum somehow nobody points to these books as sources of deep insight, and we just continue presenting the same things. And I was just curious what your thoughts on that was, because these books were so inspiring to you, and it's Feynman, so it's like clearly some gold in there.
Yeah, right. No, when I teach, I go back and every now and I'll reread a section or do something like that, and bring it into class.
You do,
yeah.
Okay.
Just it's a good second physics course, I think.
Okay.
And I don't think it worked out at Caltech so well.
I see.
And I think this is just from the preface. I think the TA's got a lot out of it.
Yeah.
I think it's I've heard it. I've heard it's like taking field theory, right? The second time is much
Yes.
better.
Yeah.
Right.
I see.
Right.
I see.
You're
Right.
just, for him, right? He thinks he's teaching at this basic level, just because of his comprehensive grasp of the way nature works, right? And trying
Yeah.
to get, oh no, this is the simplest way to look at it, right? Which is so much more advanced
Yeah.
than what you would a normal person would just get from reading physics text. So anyway,
I
so
see.
that was that made a big impression. Anyway, just so I kept reading. I mean, I just did a lot of physics problems and worked
Yeah.
on.
You did the physics problems for just out of curiosity.
Yeah, just to make sure I understood what I was reading.
Okay. Yeah.
And they're fun to
Right.
think about, right? It's just
Yeah.
sort of,
Yeah.
keep my mind active, right? Keep,
Yeah. Yeah. Yeah.
you go there and you can read all those. I read War and Peace, Moby Dick, and all those all those long books you don't have time for, or I didn't have time for in college, and then yeah. So then that was that. I came back from that, and then I was thinking about what to do, thinking about applying to grad school, and I called up Martin Pomerantz, and so I've been working with him and wanted to talk about grad school, and he asked a bunch of probing questions, and is that what I really wanted to do? Was I ready for it? And I decided I wasn't quite ready for it. So I went and I'd saved up a bunch of money there. And so when my latter part of growing up was in Maine. So I went back to Maine. I'd sailed my whole life. And so I went back to Maine and I bought an old wooden sailboat and started fixing that up. And my goal, I really wanted to get to the South Pacific. And,
Okay.
Anyway, so I bought it, and the boat was a wreck. I paid way too much money for it, and there was no caulking. You could see through every plank. And anyway, I just was whatever, young and naive, and I could fix that.
Yeah.
So anyway, we did over the summer. Had a bunch of friends come up, and we all got together and got it going, got it back in the water. The boatyard, made friends with the boatyard guys, and they were fun. They were just Mainers and fishermen, but they were and worked in this boatyard, and they were great, and they really helped out a lot and taught me tons of things about boats and engines, and they were of that sort of classic old Maine fisherman mold. You can fix anything, you could make it work, and you just figure it out. And
Yeah.
and anyway, so did that, and then sailed down to Florida with some friends. Okay. And the boat was leaking a bit, so, and I mean, this was like sailing, so it'd sail and get a job, and we had no money. Right? Sail and get a job. Sail and get a job.
What type of job?
Just carpentry.
Okay.
Ask if somebody needed help. Other connections from. I could have just worked on every little thing, and then finally had to get a real job. Well, and so I sailed into, and boats are expensive, right? So it's just always, and so sailed into Fort Lauderdale, and got a job in a boatyard there, and I had to sister the ribs, so they let me keep the boat there for free, and paid me, I don't know, minimum wage at the time, and
Yeah.
so I just worked. And I was a bottom painter, and then I was a rigger, and so worked my way up through the ranks there. So I just worked on the boat and worked in the yard and hung out in the boatyard in Fort Lauderdale, and you can imagine what that's
How
like.
long was this?
That was 9 months.
Oh, wow.
And then I got everything together and sailed through the Bahamas down to the Virgin Islands.
Yeah.
And
By yourself or with friends still?
with friends,
Okay.
other friends, and these are all old friends, different friends over the
Right.
years. And then,
Yeah.
and that time the hull was in pretty good shape, but the rudder broke off north of Puerto Rico, and that was a bummer. And so we managed to sail in with the sails into Charlotte Amalie, and I got a job there as a carpenter, and just and that was great. So I was that was real. But I'd say more rigging is rigging, and carpentry was at sort of a different level. I'd done some before, so I knew it. But we built teak bottle holders and things like that for sort of custom woodwork in boats.
Right.
So I did that for 6 months, saved up money, fixed the rudder, and then.
And you were doing no physics in between all
Oh
of this?
no! I actually I kept doing physics. I mean, I know
Okay.
official physics, but I
Yeah.
I sort of
Like your
slowed
Feynman.
down. But I
Yeah.
finished Feynman. The one I remember reading was it was semantics. I still have it. I think is it was Szymanski's Heat and Thermodynamics. I still keep it because I still have my solutions from when I was sailing. Anyway, so I kept doing, just to make sure I didn't get too
Yeah.
weak.
Yeah.
You
You
mentally.
forget it, yeah.
Yeah, no. So I kept, but not quite with nowhere near the frequencies when I was in the Antarctic. But I kept doing physics problems and reading physics, and I had Misner, Thorne, and Wheeler on aboard, and so I kept doing that, and then fixed the boat up, built a new rudder, and this was with my college roommate, a guy named Jed West, and then we took off for the Panama Canal, and then it was about and the weather. I've been in a lot of storms since. This wasn't that bad. It was just a little rough, and it was rough enough that the water was coming over the deck of the boat. I remember because this was back when we navigated with sextant, right? So this is because I remember was taking a noon shot with a sextant, and the and a wave, the top of a wave hit me, and it's like it's like screwed out. It was a plastic sextant,
Okay.
right? And the lure was you could. So I had this plastic sextant, which wasn't too bad, and the lure was if you bought a Timex watch, a crystal watch, and you never took it out of its case, that was a good enough chronometer, and it turned out it's true. So that was our chronometer, and then with the sextant, we do these noon shots. But anyway, I got hit with a wave, so I know it was at least that rough. But then, the first thing that happened was, we were sailing downwind, and we just got, rigged wing and wing. I don't know if, jib goes out one side, mainsail goes out the other side.
Okay.
And we just got this weird wave came, and the first thing that happened was not the rudder, the steering mechanism broke next.
Oh.
So it's like, oh shit, I've been through this before. Anyway, so then we had rigged the boat to steer it with the sails, but downwind, right? Because you follow the wind goes from the Virgin Islands to the canal, so you can just steer downwind. So we're steering downwind with the sails, wing and wing, with the jib out, and then we got this wave, and it just came over, and it lifted up the boat such that the jib, just the it was a staysail on the jib, came up, and one of the hanks, those are the things you use to put the sail on the stays, caught and ripped the sail in half. So
Oh,
then
no.
we couldn't balance it, so we couldn't steer downwind. And it was, I remember when that happened, so the sail was split in half. It was that night, and I was just like, okay, this is it. I'm going to grad school. It's like, I'm gonna sail into Boston, and I'm gonna apply to grad school.
Yeah.
And then so
Why'd you pick Boston?
oh,
It was just
MIT, Harvard, all those places were there, and I had no idea what was going on. I was just I was so naive about how this whole process worked. And I was just like, oh hell, I'll just go there. And so then I fixed that, and we had a great time. We sailed into Jamaica with just the jib. With just the mainsail, and a broken steering mechanism. And so we'd gotten pretty good at sailing. We sewed up the sail, but that took a couple of days to get it sewn up. But we sort of hove to and made our way into Jamaica. And I'll just tell you this one. I mean, we had Jamaica on our chart was like this because we weren't going to go to Jamaica. We had no electronics, nothing like you have today. Anyway, we made it into Jamaica with my friend up in we had Ratlins, up in the Ratlins, looking, down through the water for coral heads and things. And then we'd rigged a thing we could steer. It's like a big paddle that hung out the stern, so it could move the stern of the boat over. Anyway, we made our way into Jamaica, fixed the steering mechanism there, and then the Caymans and Belize and Cozumel and Key West, and then Boston. So I sailed into Boston, and I've forgotten the exact sequence. I should go back, but it was roughly like this. So I sailed into Boston, got tidied up, saw some friends, and who I still see every now and then, but because anyway, I've been sailing. So anyway, and I walked into to MIT, and I went to the graduate admissions office.
Yeah.
And I said, "Here's my," and it was closed.
Uh-huh.
And and I was looking through the window. I was like, oh damn, and the guy behind me said, "Can I help you?" And I told him, I've been sailing. I was in the Antarctic, but I was a physics major, and I want to apply to grad school, and da-da-da-da. And he said, "Do you have a CV?" And I said I wanted to get a job before, because it wasn't quite applying season then.
Okay.
And he said, "Well, do you have a CV?" And I said, "No." He said, "Well, come around, and my assistant will help you make one, and we can distribute it to the department and see if you can get a job."
Oh, wow.
I know.
That's so nice.
It's just Herb Bridge. Turned out he was the head of their Center for Astrophysics at the time.
Oh my God.
But I was so embarrassed. I was so embarrassed. I went and I typed up my own CV, and came back, and they circulated it, and I talked to a bunch of people. Most because I'd eventually end up there, but most people just said, "Well, why do you want to stop sailing?" That sounds pretty good. It's like, oh no, you don't understand. Anyway, so I talked to a bunch of people, and I couldn't get a job. No one would pay me.
Just for like a regular job, not physics.
No, I wanted to be a research technician.
Right. Okay.
And work in a lab.
Okay. Yeah.
I was just figuring, sure, I must.
Yeah.
I mean, here I've been hustling.
You have experience as a technician.
Yeah, I've been hustling all these jobs, from doing drywall work on the way down to Florida, and then Florida get a job, and then land in a new place and get a job, and then I just figure, okay, I'll just land in Boston and get a job.
Yeah.
And then, so anyway, I got a list of names, And actually, I'd forgotten this part till he reminded me. One of the names was Ray Weiss, and so anyway, had his. I went to see him in his lab, and his lab was closed. The door was locked.
Mm-hmm.
So I went around, and I'd totally forgotten this till he reminded me a couple of years ago. I went around, and I could see there are people in the lab. So there's a little barbed wire topped fence, and I climbed over and rapped on the window. And they came and let me in.
Wait,
anyway,
so this is like an outdoor,
yeah,
like it was its own building?
it was Building 20 at MIT.
Oh, is that teared down? Or is
Yeah,
that still...
it's gone.
Okay,
It's gone.
I
It's
see.
now the status center. Whatever. Anyway,
Oh,
so he let me
okay.
in.
That's a famous building also. I mean, the Building 20
Building
is
20,
like...
right.
Yeah.
So then he let me in, and we talked, and he said he couldn't pay me, but
Yeah.
I mean, this was just he said I could work in the lab,
Yeah.
and like right off the street.
Yeah.
So
Not worried that you would break some expensive equipment.
no. Anyway, he gave. So I got a job as a carpenter in Boston, installing greenhouses. That's what I did in a day, and then at night and on weekends I'd go and work in the lab, and then and he gave me a project, and I worked on it, and it's a helium cryostat, and it leaked, so I had to fix that, and then it was actually measuring the noise of transistors, the voltage and current noise of transistors, and it worked out, and figured stuff out.
Was that for a bigger experiment? Or?
It was It was related to the Kobe experiment.
Mm-hmm.
So it was, and I think my the usefulness of what I was doing was long surpassed, but it was a project, so I kept doing it. But it was, but they had used these transistors to in something 47As. Anyway, they were really low noise FETs, and they just wanted to figure out the current and voltage noise. So, and it's hard to measure when it's low noise. So, so you have to submerge a resistor in liquid helium to keep it cold. And anyway, so da. So that worked out. I studied for the GREs. I said, okay, now I better take these things seriously. So I studied for them, and I did just fine. Well enough to be even admitted. I wasn't admitted here, but at least at that level. And then, and I applied around, and I got into MIT. Just because I'd sort of shown I could do experiments, and that was it. And I was never. And the advice I got, and I give this to everybody from a liberal arts school, is, and Ray just told me, retake our undergraduate senior level courses.
Mm-hmm.
And that was really intimidating. All those smart MIT undergraduates, was right off the boat.
Yeah. Literally.
Just like, oh man. Anyway, I did fine. So I really studied hard. I did fine.
So you spent like your first year of grad school retaking senior level undergrad. Okay.
E&M, quantum.
StatMech.
I must have done StatMech, yeah.
Okay. I guess, yeah.
I
You were
didn't do
doing
one
that
of
on
them,
the boat, so.
So it was, that's what I did, and learned a ton.
Mm-hmm.
And
but then you had to take grad courses too.
Right. Anyway, so then I just started working my way through the program.
Yeah.
And I was in phrases that are used today, like there's this imposter syndrome. I definitely it's like, what am I doing here? I was always worried that I just wouldn't be able to make it through.
Yeah.
I always had I actually was in the process of replacing my boat engine,
Uh-huh.
So I had my old engine underneath the lab bench so I could work on it. Anyway, with my spare, I never got around to it, but it was that sort of lab, right? I can't imagine that now. It was a lab.
Yeah.
I had my old diesel, a Isuzu diesel in there. And then, anyway, I just started working on experiments.
I remember you said he gave you two options.
Yeah.
One was the gravitational waves or CMB.
Yeah. So then, so it was his lab, and Steve Meyer, who is now at University of Chicago, had just joined there as a new faculty member, and so I'd been there long enough, and Ray just asked me one day. He used to smoke a pipe back then. He said, "What do you want to do? Which experiment? What do you want to do? Which experiment?" So he was just starting up the gravitational wave business and building a prototype for what would become LIGO, and then Steve was starting this CMB anisotropy experiment. He said, "What do you want to work on?" And then he didn't let me answer. He just said, he just said, "Work with Meyer." So that was it. So Steve was absolutely, it was great. I was his first grad student, so he got lots of attention and learned tons and tons and tons, and we did an experiment. We did an experiment to go measure the anisotropy in the CMB.
Yeah. Did it finish?
Yeah.
In grad school, or was it one of those longer scale experiments?
It turned out so. This is a balloon-borne experiment with bolometers and helium-3 fridge, which it was definitely one of the earlier balloon-borne helium-3 fridges. And it was to look for the large-scale anisotropy in the CMB, so really after the quadrupole and the octopole. And we built it, and we flew it in October of, I think it was 88, must have been the first flight. And we launched it, and I remember there are a few little issues with it, but it was working.
Okay.
It was, the balloon was lifting it up, and we were just getting, it's going to be an all-night flight. It's not like, nowadays there are these, week-long flights. It's going to be an all-night flight, and you're talking about just ordering in, let's get some pizza. But we were trying to, you launch it flat, and then we tipped it up to 45 degrees and had a calibrating membrane that would rotate in front of it. And we were tipping it up, and we knew we moved, but the angle would just drift a little bit. It's like, what's going on here? Why isn't it's a little more stable? And the head of the balloon base, Danny, the head of the flight crew, Danny Ball, I remember he was in the other room, and he leaned in. He said, "You're on the chute." And we, and apparently the balloon, it reached altitude, and as it reached altitude, it expands, and it had burst.
Oh no!
So it was, but we got 8 minutes of data.
Yeah.
And before it burst, and with it stable enough. And and when it burst, it was really something, right? So here's this balloon falling down from 100,000 feet and through all the, there were airplanes, all air traffic control was stopped. We didn't know where it would land. Actually, we eventually it was coming down over Clovis, New Mexico, and it didn't hit anything, but it ended up upside down in a cornfield, because they couldn't undo the chute, dragged through the cornfield. So here's my what I've been working on for 5 years.
Yeah.
Just,
Yeah. 5 years
I looked
for
out,
8 minutes of data.
Yeah, I looked out, and I remember seeing it. It was, I have a picture of it. It's upside down with corn stalks sticking out of everywhere. It's like, oh crap. But anyway, it we gathered it all back and drove it back to MIT. But then, yeah, with those 8 minutes of data, to give you an idea of how sensitive it was, we set the best upper limit on the anisotropy at those angular scales, and found that interstellar dust did not follow a nu squared emission law, which is what you think, because dust grains are really tiny, and so their emissivity should go like the wavelength squared, because whenever you have an object much smaller than the wavelength, it should follow that. That its emissivity should go like that. But we found it didn't follow that. So either there had to be multiple temperatures that did follow that, or the emissivity of dust grains had to not be what you'd think of theoretically. I mean, it's just like fundamental theory, right? Is just if you have an emitter that's way smaller than the wavelength, it goes like nu squared.
Yeah.
So that was my thesis. And we saw it looked to be clouds of ozone. We couldn't quite tell, but I think that. So anyway, that was my thesis. So 8 minutes of data.
Yeah.
And then we flew it again the same month I graduated. We refitted up, flew it again, and this time it worked. And we got data all night, and then we analyzed those. So it was October '89, that flight was. And that, so we made a map, and we knew there was some kind of anisotropy in there, but we couldn't say it was the CMB.
Yeah.
And
why not?
Because at the time, because we only analyzed one channel at a time, we couldn't tell it was some kind of dust, whether it was atmosphere.
Yeah.
We had enough systematic checks that we knew a bunch of things it wasn't. We thought it was on the sky, but we couldn't just say this is the CMB anisotropy.
Right.
And so then over the following, I guess it was two years, we just kept analyzing the data.
Okay. And this is post-grad school.
Post-grad school, so I was a postdoc. And
okay,
we
yeah.
were still.
You stayed there as a postdoc?
No, I was there and here.
Okay, okay.
Yeah, so I started up as I've forgotten how long as a postdoc, but anyway, as a postdoc and then an instructor.
Yeah.
And then, and anyway, we analyzed the other channels. We kept looking for systematic effects. And then we knew we had the signal in our data. We didn't know what it was.
Yeah.
And then a couple of things happened. We found there was a bug in the code that we were using to determine the statistical power of the signal, and we fixed that, and then COBE came out, and we cross-correlated with COBE, and we found that this dominant signal had all along been the CMB anisotropy.
Oh wow!
So that was pretty exciting.
Yeah.
That was actually that was a lot of fun work. So Ken Ganga was the leader of that analysis, but anyway, he was my first grad student here.
Oh, okay.
Yeah, so that was just really fun.
Yeah.
And anyway, so that was really exciting.
Yeah.
So we definitely had it. It's one of those things. You have it in your data. We had the data well before COBE launched.
Yeah.
But we just didn't. We couldn't just. We couldn't say it was the anisotropy. So I guess we could have BS'd it.
Yeah.
And then cross correlated later, but
Yeah.
that's of course that's not right. So anyway, that was really neat. I mean, what a way to
Yeah, that sounds like a
start.
Amazing grad school project that worked out perfectly. I was just thinking if you picked gravitational waves, that would have been a different story.
I know. It's so funny. Or if Ray had picked, I would have done whatever Ray said.
Right.
What if Ray had picked it for me?
Yeah.
No, it's just, Steve was a new faculty member and he needed students.
Yeah.
And that was it.
Yeah. Wait, I remember you said Nergis was in your cohort, like your same year? And
no, she was a couple of years after me, if I remember.
Oh, okay. She went into gravitational waves. And I remember she had a funny story also. But then it's like how many years later they actually found it? 30? I don't.
Yeah.
Yeah.
Yeah. No. Yeah. That was quite. Yeah, that was fun. I remember her working with her on an early project. We had some crazy ideas on how to make filters and that sort of thing, and she, that was a fun lab.
Yeah.
And Anyway, so then I came here, and then in 1990, so. Been here since.
So when you finished that, how did you decide what to do next? And because it seemed like a very good stopping point for that project, and I don't know, you have to think of new things.
Right.
Yeah.
So what happened was we had I was working. When I look back, I was working really hard then. So we flew in October '89, that balloon. We then flew it in May of 1990. Rebuilt an old receiver and took that. This is with Mark Dragovan, who was on the faculty here. Another helium-3 based system. Took that to the South Pole for observations in December of 1990. And our first son was born in September of 1990. And then the receiver from my thesis was redone and put in a larger telescope. And that was, I think those were sort of the early 90s. That was another balloon payload that flew again. And then, but when we were in the Antarctic, the Santa Barbara group, Todd Geyer was down there, and Peter Meinhold, they were working with Phil Lubin. And they were, bolometers measure up near a couple of millimeters. That was our lowest frequency. 150 gigahertz in there. And they were measuring down 30 gigahertz with these new coherent amplifiers that had been invented by Marian Pospisalski at NRAL. And they showed them to me, and it's like, wow, those are so much simpler we're doing, and they're so sensitive. So when I came back, I started thinking about those. So I was already here then, so then I started thinking about those instead.
Mm-hmm.
And then proposed around that time in the early 90s, as shall get the exact date sometime, I was walking by Dave Wilkinson's office, which was this office.
Whoa.
And then and I just remember walking by the door, and he said, "Hey, Lyman, you want to work on a satellite?" Measure the CMB. It's like sure. I mean, this was before the discovery, right?
Oh,
of the anisotropy.
Yeah.
This was early on.
Yeah.
But we all knew it was a really good thing to do. So, and then separately, it came to him and to write a proposal to use these hemp amplifiers to make a measurement from Saskatoon, Canada, because it was a good dry site that he and Peter Timby had pioneered. And so we wrote a proposal about testing hemps and hemp amplifiers and a new configuration came up with, and in Saskatoon for eventual use on a satellite. It's actually for ground-based observation. It was funded by NASA because of its potential use in a satellite.
Oh, okay.
So,
yeah,
and probably because Dave Wilkinson was on the proposal.
Yeah.
but it was anyway. We got that, and we did a series of experiments with hemps from the Saskatoon experiments. And then we didn't use the design in the proposal, but then when we went to propose WMAP, we did use that design. So then that was, of course, there was I should say propose a satellite, and that was that was all going on then.
Mm-hmm.
It was so like what, yeah, it's a good ending point, and I was definitely looking for other experiments to do, but it was at the time, it was just also so exciting.
Yeah.
You know, the anisotropy had been discovered. This was before we knew that you could figure out all the cosmological parameters. I mean, that would really come in the mid to late 90s.
Mm-hmm. Mm-hmm.
And so there we were, you know, just doing different measurements. I think it maybe done 4 different measurements by that period with different technologies.
Yeah. Would you say experiment was ahead of theory then?
Yeah, I think they've gone hand in hand throughout.
Okay.
You know, I mean, in some sense, you know, here, so it's in, I think it was 87, Bond and Astafiew wrote that paper based on stuff that Peebles and you and Sunyaev and Zildovich had done. But they predicted the CMB power spectrum.
Right.
It's beautiful, right? It's just, there it is. They predicted what the anisotropy should look like.
Mm-hmm.
So in that sense, it wasn't, but what no one knew was what the model was, if that was the right model. If no one knew the geometry of the universe. No one knew if the universe was reionized, so we couldn't see this. No one knew what the foregrounds were. None of that was known. So it was like this. It was just. It was just constant discovery. And there were, I should say, and there were a million theories. That's the one we remember. That's the plot we remember because it turned out to be almost right. But oh my God, there were just there's cosmic strings where non-gas structure formation didn't happen from adiabatic fluctuations. Peebles had isocurvature fluctuations in which the spectrum was completely different from what Bond and Astafiew had. You also had the adiabatic fluctuations. So the number of theories, so I'd say, in some ways, there are just tons and tons and tons and tons, but we didn't know what was out there. We didn't know what was going on.
Right.
When we proposed WMAP, we didn't know the geometry of the universe.
Mm-hmm, mm-hmm.
And even if we could see second and third peaks, right, if there had been lots of reionization, it would have wiped them out. And so it was just... It was just we just slowly figured out we could learn more and more and more and more things.
Yeah.
And it was just exciting. And we knew how to do it.
Right.
So,
yeah.
So
that sounds like a good situation.
Yeah, no, it was great.
Yeah.
Yeah. So anyway, we made tons of measurements, figured lots of stuff out.
Yeah.
And then WMAP worked well. And
So like amidst all this, I'm just wondering, when I think about people sort of like in that similar point in their career, when you were doing this, uh, I think a lot of people now, it's like this postdoc, will I get faculty?
Right.
You know, like how did you feel navigating that uncertainty? Did it feel uncertain to you, or did you just always was like physics questions, like I'll just keep on doing physics regardless, I don't care?
I cared, but it was also like, let's just do physics.
Yeah.
And it was, I mean, those were very different days, right? So, oh boy, and I was so naive, and I had no idea how any. I'm still pretty naive, I'd say in many ways, but then I really was, it dawned on me a little later that if Ray said this guy should get into grad school, I would get into grad school.
Yeah.
That sort of thing.
Mm-hmm.
I know I had good letters from everybody.
Right.
I'm sure that, and I had good grades and I had good GREs. So
Right.
But it took that extra thing. So but then the path from there. So, let's see. I don't know if I should say this. Well, I'll tell you. It's how broadly. I mean, I had a offer here, even as I was finishing up grad school.
Okay. Yeah.
And it wasn't official. There's no official offer.
Yeah. Yeah.
It's just, why don't you come here and join our faculty?
Okay. Yeah.
But at the same time, faculty positions here are like postdocs.
Oh. Okay.
It's not like it isn't like now.
I see.
The tenure rate was really low.
Mm-hmm.
It was, and I didn't really care because I was coming here to work with Dave, but there were two other CMB faculty members when I was here. It was that sort of thing.
Yeah.
Right. But
so you weren't sure. It's like, why would Princeton give tenure to another CMB?
I was thinking less of that.
Yeah. Okay.
And this is just the next step.
Right.
And and there's a two-body problem.
Mm-hmm.
My wife's a physicist,
Mm-hmm.
and she's navigating all that. Anyway, it was complicated, but the physics was so great.
Yeah.
I just couldn't not do it.
Yeah.
So
yeah.
I didn't think about it like that, and if it had all fallen through, like, I don't know what I would have done, but anyway, so I did, and these experiments went well, and I made it through the system.
Yeah.
And so, and just kept doing them.
Yeah. And then you became head of department.
Yeah.
At Princeton.
Yeah. Right. Yeah. That's more, and I think it's not like being the chair of an English department or a medical school department.
How so?
It's not as far as I know.
Yeah.
It's not a sought after position.
Oh. Okay.
I don't think anyone wants to be chair. It's
Okay.
more like you're part of a department, and it's a duty, right?
Yeah. Okay.
If you want to keep it going, if you can organize things, it's more like it's some responsibility.
Yeah.
I remember Dave telling me fairly early on. He said, "Well, you're going to have to be chair."
Wow.
And he said, "Okay, so don't let the library take the Tiffany window, and make sure you always thank the gardeners for the beautiful plants." And the rest, because he had been chair.
Okay.
Right. And
Yeah.
Dickie had been chair, and he had been chair, and he said, "You're going to have to be chair." And so it was already, okay, I'll have to do it someday. And then finally my day came, so I did it. But
it seems like you do have this like sort of, I don't know, like you've shown that you care about mentoring, I think, and care about students, and I think you generally show that you care about people.
Yeah,
So
I do care about people.
yeah, I mean, in a
So-
way that's like more than other professors, I think.
Oh,
So
thank you.
yeah, and so I don't
yeah.
know. Did you see that
It's a
role? As,
character flaw.
yeah. Did you see being chair as like an opportunity to do something, I don't know, different or I mean, because you did do things later on, I know, like create the bridge program and stuff, but I don't know what you were thinking of back then. Yeah, back then it was just like
Do
the
I?
duty.
In some ways, it's been a while. I mean, uh, yeah. I mean, I sort of, you realize there are things you can do that you just can't do as a regular faculty member.
Yeah,
I mean, there's a certain amount of steering in a direction. There's a certain amount of steering that goes on
mm-hmm.
just by little corrective actions. And probably the biggest thing is don't screw up the department. Try not to, and that's probably the number one thing. There are other obvious things. I mean, I've forgotten how many women were in the department at the time. I did that. I think it's at least Suzanne, and I did think that was important, just to be relevant. I mean, at the minimal level of diversity, which we are still, I'd say, failing might be harsh, but we're not doing. We could do much better at,
Mm-hmm.
and I think we keep striving. But we keep trying.
Yeah.
But
What motivated you to like create the bridge program and be the mentor?
Oh, that was just. At first, I can back up a little bit. It was so here when I was just doing research. I mean, I was really just doing.
Yeah.
I was teaching. Teaching was fine. I love
Right.
teaching.
Yeah.
I love working with students. But I was like, boom, 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 boom. I really was like, okay, I want to get this result. Okay, what's going on? Let's learn this. Do this. Do this. Do this. Do this. Do this. Do this.
Yeah.
And then I think somewhere in there, I went. I may have been chair, probably was chair early on. Just for always being interested in questions of civil rights and discrimination, and I went to they were combined back then. It was a meeting for the Black and Hispanic physicists. So it was a combined group. And I just went to learn more about the challenges. Why were there no African American students at Princeton? Or why were there so few, or so few Hispanic students? And why are there so few in physics? And I remember and just trying to figure out why that was. And sort of also think, and it really struck me one time, just flying out of L.A. and just going over this massive, millions and millions and millions of people, and just thinking, why aren't there more physicists from here? What's going on? What is it in people or nature or society? Because the raw talent's there.
Yeah.
I'm just like. That's for me. That's a given. It's like it's impedance matching. Right? What is it?
Yeah.
It's what is it? The way we grow up, the way we're taught, the way we're learned, that makes us want to be physicists.
Yeah. Have you figured it out?
No, not at all. But I just know I know and I think going to that conference, I just saw the barriers.
Mm-hmm.
In a whole new way, and just tried to see, what could be, what Princeton's got resources to see if it could use some of those resources to try to make an effort to improve things. The other thing that really struck me from the conference is just the number of students from underrepresented groups is so small that if you can work with one or two people, it makes a difference. It's just, I mean, it's not like you need a big program, or you need a movement.
Yeah.
You don't need to start that. It's just human. It's just people, and it just takes a few, right? The number of, say, African American physicists in the U.S. is not that many, right? It just takes a few. So, I actually went with Chris Eisgruber was provost then.
Okay.
I just said,
Yeah.
I want to try to start this program, and can I get some money?
Yeah.
And he said, sure. That was it. He said,
Nice.
yeah, that was it. And so he gave us some funds to start it. It went going for a few years, and students have done well. I've lost track of one, but the rest are doing well.
Okay.
And
is it still going? I don't.
No,
Okay.
it's the graduate school now. It's more of a national movement.
Okay.
And the grad school has their own program.
Okay.
Which I don't think is that well meshed to physics.
Okay.
I think, but it's fine. You try a lot of things.
Yeah.
I think for just based on, and you can try to plan these things based on, I don't know, you can read studies or not. For me, I just know that I don't care where you took physics. If it wasn't at a university the chances are really, really high that you're going to need to retake your senior level courses, because you're not at the level of, basically all of you guys. the grad students that come in here are just amazing. So, and there's a big gap between there and what your, even if you go to a top liberal arts college, what you get from that. And then, okay, so you don't go to a top liberal arts college, you go to a state college, right, or a smaller university college. It's just, you're not going to, I don't care if you had the same textbooks.
Yeah, right.
You're not going to be challenged in the same way. You're not going to be tested in the same way. You can get all A's. It doesn't make any difference.
Yeah.
You're not going to be forced to have the depth that you are in other places. And it's not for your fault. It's the context isn't there.
Yeah.
So I think for me, any program has to be 2 years. It should plan to be 2 years long. And some students can, come up to speed quickly.
Yeah.
Do it if they're motivated. So
yeah.
Anyway,
it's interesting that you say that. Yeah, because people do say we use the same textbooks and stuff, and as like a marker, but I don't know the problems and the amount that you go through, that I see these students go through as they TA. it's like it's kind of crazy that how they do it.
Yeah. And right, and just what comes out the other end. It doesn't make any difference if you use the same textbook. You can be. It's the type of questions you're asked, the expectations on problem sets, and the peer group. If you're a star student in one place, you're that's it.
Yeah.
And it's not like being here where there's 10, 15 star students each pushing each other to go a little deeper and
right.
Or here I say here, but of course any high level undergraduate place. Anyway, so and then that's just the academic side. The social side is just as challenging. And And I mean, I got a glimpse of it once. I mean, I was so hard headed it didn't affect me. But I remember my grandfather once asking, "Why would anyone study physics? How are you going to make money?"
Yeah.
You know.
Yeah.
And I think, and I heard this at this Black and Hispanic Physics Society. Just the stories of, like, my family has no idea why I would want to study physics.
Yeah. Yeah.
Like, just none. No, there's no support structure. There's no appreciation. There's nothing. So, and then you add on all this, the other social elements. The challenges are enormous, and they're enormous, and so in multiple dimensions, right?
Yeah.
So,
Yeah.
and I think any program has to address all those. I'm not sure we were very good at addressing the non-physics ones.
Yeah.
But any I think you need some program that tries to work that in.
Yeah. Yeah. I mean, for me, growing up in Trinidad, like even my physics teacher in high school was like, why would you go and study
Yeah,
physics?
there you go.
I'm like, what? And everyone,
Right.
my friends' family, it's like I had gotten lucky and won the scholarship, and they were like, why would you use this to go and study physics? And it's just, I don't know. Yeah, it's because it's
Right.
interesting. I love
So
it.
you're bullheaded as well, right? Yeah.
Yeah. So, yeah,
Yeah.
completely relate to that one.
Yeah. So that's a lot to, right, there you go, right? You come over anyway.
Yeah.
So what was your school like in Trinidad?
It was a very small school, like 600 people over 7 years. It's kind of like the British system.
Okay.
It was like, I think it was a good school in that the students compete with each other and push each other. But they all go into engineering, medicine, mainly engineering and medicine. Yeah. And I was just doing well in physics because I didn't have a good memory, so I couldn't do well in other things. But then physics and math started to kick in, and I was like, I love this.
Yeah.
So
Sounds like a very similar
Yeah.
experience.
Yeah.
Yeah. Well, and here you are. It's
Yeah.
great. Wow.
Yeah. Even my parents were like, "You're not going to study physics." And then when I got the scholarship, it was like, "It's not your decision." So, yeah. So, yeah.
Yeah.
But anyway, speaking of, apart from you being a professor who like cares about people more, I think, on average, I feel like as a professor, you also work more than other professors in a different way, probably, because I think it's very uncommon, at least in my experience, to see, especially in experiment. I think the professors turn into lab managers frequently, and sometimes some of my friends would say they came in on the weekend and they were like, Lyman was like in his lab working on electronics or something, and
Yeah, right.
you're still so like involved in the project, and why is that so different for you? Or like, what is it?
I mean, I was like,
Yeah.
When I was, when the head of the ACT collaboration for a long time, and that is, and there's less of that. You do get more towards the managerial side, and it's now, so now Suzanne has taken that over, and Mark Devlin at Penn, and Joe, and so yeah, it's more like going back to my roots, I guess.
Do you enjoy it? It's like,
yeah.
yeah.
Yeah, it's I mean, now it's sort of we're trying to get this one experiment out the door, but I think
The
I'm
Axion.
finally, no, that one, that's longer term. I
Okay.
hope we have I swear is my last CMB experiment.
Okay.
I don't know what number it is. I haven't count, but it's a new instrument to search for B modes, primordial B modes.
Okay.
And this is now with Sam and Joel and Yuhan, and we're very close. We'll get that down to Chile and then analyze data from it. It's just like one of these. There for me, what drives me. There are a couple of great big questions in the CMB, right? One of them, are there gravitational waves from the birth of the universe at some measurable level? And this experiment and its sister experiments should be able to reach that level. Just have to get there. So I'm interested just because it puts so much pressure on, on inflation.
Yeah.
Different models of the early universe, right? And that's, did inflation happen?
Yeah.
I don't know.
Yeah.
But if it, if we can get down to the level, we're already past the level where everyone thought we'd see gravitational waves, of
Yeah.
course. Okay, so everyone retool, gets down a little lower. Okay, retool, get down a little lower. And then I think if we get down to this sort of next level tensor to scalar ratio of, less than of order 10 to the minus 3, it'll be, I think inflation will lose its luster. You can always come up with another model, of course.
Yeah.
But I think it might it might help propel different thinking.
Yeah.
Right.
Yeah.
And there's so much we don't know, right?
Yeah.
that about the cosmos that it'd be wild if we had that model nailed down right now. And anyway, so
Yeah.
Anyway, we'll see. It's a measurement. We'll find out.
Yeah.
The signal could be there, and maybe not. I think we'll do it. But that's my last CMB experiment. So we'll get that out the door. So that's what I'm working on mostly. But then the Axion experiment is just with Saptarshi and Roman. That's just. I'm really looking forward to working on that. That one's like really going to be like going back to the roots, because it's a lot of new physics for me.
Yeah.
It's small. It's just a few people.
Right.
It's not like the B mode experiment, which is a part of a $100 million project and whatever. A whole bunch of people with their other ideas about how it should be done and all that sort of thing.
Right.
This is just small. It's neat. They're really neat techniques, experimental techniques. It's a neat open question, and it's some combination of an interesting question and really techniques that are really at the forefront of experiment. Trying to evade standard quantum limit at some level, although we won't need that for a little while. We're starting on it now. So that'll just be fun.
Yeah.
So.
But is that experiment in competition with others?
Not really. It's too early. Yes, but not really.
Okay.
Because it's
still different.
At this stage, it's much. I mean, at least in the U.S., I know all the groups.
Yeah.
And we definitely. We would absolutely share anything we learn with everyone else.
Yeah.
And vice versa.
Mm-hmm.
And I don't think any of us are expecting to see the Axion tomorrow, which puts much more of emphasis on how to do the experiment and do it right and plan for a healthy, future. Because these steps are important, right? It really is. It looks like it's a way to go probe sort of energy scales of fundamental physics beyond what you could ever get in a ground-based accelerator, and eventually push down. Although the road's long, but it looks doable to what you could really see a QCD Axion.
Wow!
And so it's possible.
Yeah.
But it's the steps are now. That's when you get to that scale. That's a big. Many multi-million-dollar experiment.
Okay.
And so we're in the first stages of that. But I mean, I know at least in the U.S., the other key players in this. Not all of them, but I guess indirectly I know them all.
Yeah, I only ask because I know of the one other one, the Abracadabra.
Yeah, so that's sort of joined, right?
Oh, okay.
Joined
with, I just know MIT
DM Radio.
What do you mean?
And Stanford.
Oh, okay.
So DM Radio is heavily abracadabra.
I see. Okay.
Right. So I think that's all. I don't know. So that's all sort of come together.
I
and
see.
like what you know what I mean, actually, not infrequent contact with Lindley
Mm-hmm.
and then with Kent Irwin, and so they're all very supportive of what we're doing. So it's not. It's really.
It's not a competition.
It's nice. It's
Yeah.
not. I'd say no. It's not. And we all want to do well and figure the things out.
Right.
But it's not. It's not. Not like the early days of CMB.
Okay.
No, it's a different phase.
Yeah. So can you tell me this story with Wheeler?
Okay.
Yeah.
Sure. So, yeah, when I was in, when I was an undergraduate,
Uh-huh.
you know, it's like, of course, I read that book or read most of it, and actually I did a lot with. I read a lot about what Dickey was thinking and his and especially about. You know, he wrote this the papers entitled like "The Many Faces of Mach," just thinking about Ernst Mach's view of inertia and that sort of thing. But for Wheeler, so I of course knew about Wheeler. Everyone knows about Wheeler, and I came down here for an interview, and as part of the interview would go to the Bacall lunch, and Bacall, especially for a junior person, is, you know, moderately intimidating, and you'd sit in this big U table, and he'd just call on you, say what you were doing, and you know, if you talked too long or you got bored, you know, clink clink clink, and move on to the next person. But so anyway, there was this, and I was just down from Boston, right, and so in Boston there were people like I had been once, right off the street, who come and listen to talks and who have, you know, physics background. Anyway, so there I was talking, and this guy was, every time someone talked, he'd take his tray and he'd sit in front of them. And then someone else would talk and he'd take his tray and he'd sit in front of them. And I just thought, it's like, oh no, you know, yeah, it's a pretty intense place, but this is just some guy they put up with. And anyway, so I gave my little spiel, and this guy sat across from me, and the next person he moved on. And then I asked, because Mark Dragovin afterwards says, who was that guy sitting around in front of everybody? I said, oh, that's John Wheeler.
Oh.
I was like, oh, yeah.
I guess you can do whatever you want.
Yeah, it was pretty funny. I mean, he did that because he was hard of hearing.
Oh, I see. Okay.
So he wanted to hear people.
Yeah. Okay.
And that was it.
Yeah.
So.
That's funny.
But yeah.
Okay, so before I keep you any longer, I wanted to ask you one final question. Actually, two, if that's okay. I wanted to know what was any like down points in your career? Any low points? Do you have any that you can think? Oh, too many.
Oh no, they're. Yeah, they're.
One that you think is worth sharing, or some
yeah,
lesson.
no,
in there.
they're not. Look, I think it was kind of a bummer when my thesis fell out of the sky. Right?
Yeah.
You know.
Yeah.
You just pick up the pieces and do it again.
Yeah.
That's sort of a.
But you still graduated.
6 months recovery. Yeah.
Yeah.
With 8 minutes of data.
Right.
Yeah. And then. Yeah, you know, you tend to forget all those down points. There are a bunch of political personnel things, right? Those are always there.
Yeah.
No matter what you do, they're not particular to physics.
Yeah.
But scientifically, you know, there are times when, you know, you work really hard on a grant and you don't get it, or work hard on a few and you don't get it. But you tend to forget those. Those. Yeah. No, they're all sort of just things not working out in research or setbacks
Yeah.
or you just deal.
Yeah, yeah. How do you deal with it then when you don't get the grants? Just write more.
Yeah, work a little harder,
Yeah.
write more, change direction a little bit.
Okay.
Figure out what's going on. Why wasn't this successful? Who were those idiot reviewers?
Yeah. Do you ever have to review other people's grants?
Oh yeah, we do it all the time.
So they're like,
Yeah,
who is this idiot reviewer?
Exactly. Why can't they see the brilliance in
Yeah.
this proposal? Yeah, I was thinking because as I'm giving a talk next week, and I look back for this proposal we wrote, and this was for a center, and I am the kiss of death for any proposal with a center. I think I've been on 5 of them or something. Not one of them has been funded.
Uh-huh.
And it's usually the same criticism, but some form of it. But anyway, this one I remember. This was with so David Spergel and Suzanne and Mark Devlin and I were coming. We just came back from this review, and we were just so sure we nailed it. Like, oh, the check's in the mail. They're gonna love. They had to love this. And no, we failed. But then, so
Yeah.
But that was eventually we reproposed that. The NSF helped us repropose that.
Okay.
That became the ACT telescope.
Oh, I see.
But yeah, I don't know. You pick yourself up, try again. Oh, I did. Oh, I was bummed when I failed one of the things on one of the exams for my PhD.
Oh.
But that didn't last long either. You just pick yourself up and you do it again.
Right.
But yeah.
Okay, final question. You've had many students. You've had many postdocs. Like seen many people advance through their careers. What do you think? What have you seen that's like made people successful? Is there some characteristic? Is everyone different in their success?
It's funny. I'd say they're all different. There's no.
What are some things that have worked really well? I mean, have you not noticed any? There could just all be different.
I think a desire to do some sort of passion, like you can't do anything else, sort of thing, and they're all different, and it's it's working hard's a good thing, but it's not working crazy hard, right? I mean, it's probably your engagement with physics and just wanting to think about it and not. I think if it's a job for you, I'd say you're probably not going to succeed that well. You might last for a while. It's something. It's got to take you over in some way, and it can happen to all sorts of different people in different ways, and I mean the students they're really varied. I have one student who after grad school became a Jesuit priest.
Oh wow! Okay.
Yeah, and he's now back in academics, now a collaborator working on the. So he's figured out how to do cosmology.
Yeah.
And his his religion is simultaneously, and so that there he is. He's split his life like that. That's one way, but it's got the passion, right? And loves doing it. Yeah, so that's probably one end, and then people in industry, people in national labs, all doing different things in different ways. Yeah, I just think engagement and loving it, and it's probably
Is the key.
is the key.
Yeah. Okay.
So it keeps them going.
Yeah, it's what keeps you going.
It's certainly what keeps me going.
Yeah.
So maybe I'm blind to other things, but I think it does keep them going. We all.
I mean,
know,
I think
whenever,
it's clear with you. that-
Yeah. When we get together,
Yeah.
we talk physics,
Right.
Like for all of them.
Yeah. As
That's
somehow
it.
like all
There's
physicists.
personal stuff, and
Yeah.
there's all that stuff.
Yeah.
Yeah. But then it's what's going on here? What's
Yeah.
how.
Yeah. I think that's a common trait of physicists.
Yeah,
When-
yeah.
Get together and I mean I'm surrounded by physicists in Princeton also, so
Yeah.
there's some underlying passion of physics also. So
Uh-huh.
yeah, we just talk physics. Yeah.
Yeah. There you go.
Yeah.
Right? It's so engulfing. Right? Once you start to think that way, it really is.
I think everything else feels a bit mundane.
It does. It's like there are these ideas, and they're great, and they can be so sharp, and you can know things and figure things out. No matter how, and abstract things are fun, and physical things are fun. It's just
Yeah.
it's such a fulfilling way of seeing nature and the world. And anyway,
Yeah, I 100% agree.
yeah.
Yeah.
So
Okay, so I think I've used up as much as your time that I feel okay about.
that's fine.
Yeah.
Fine. It's fun talking with you.